Let me ask you something. Right now, wherever you are sitting, wherever you are watching this, I want you to close your eyes for just a moment and think about the biggest explosion you have ever seen. Maybe it was in a movie, maybe it was a fireworks display, maybe it was a controlled demolition of a building. Whatever it was, I want you to remember one thing about that explosion. It happened somewhere. It had a location. There was a point from which everything flew outward. Debris went left, debris went right, debris went up, debris went down, and if you traced all of that debris backward, you could find the exact spot where the explosion started, the center, the origin, the source. Now, here's what I want you to do. I want you to take that image, that intuition, that deeply ingrained understanding of how explosions work, and I want you to throw it away completely. Because what I'm about to tell you over the next hour and a half is going to fundamentally rewire the way you think about reality itself. You've been told, probably since you were a child, that the universe began with the Big Bang, an explosion, the biggest explosion of all time. And if your brain works anything like mine, anything like any normal human brain, then you immediately asked a question that seems so obvious, so logical, so perfectly reasonable that it feels almost stupid to even say out loud. Where did it happen? If the Big Bang was an explosion, then where was the center of that explosion? Where is the point from which everything flew outward? Where is the middle of the universe? And here is the thing that is going to keep you watching this video until the very last second. The answer is nowhere. The universe has no center. It never had a center, and it never will have a center. And I'm not saying that in a vague, philosophical, hand-wavy kind of way. I am saying it as a statement of physics, a statement of mathematics, a statement backed by every observation, every equation, every experiment, and every piece of data we have ever collected about the cosmos. The universe, this incomprehensibly vast arena of space and time and matter and energy, does not have a middle. And by the time this video is over, you will not only understand why, you will understand why it could not possibly be any other way. But before we get there, before we dive into the mathematics and the physics and the mind-bending geometry, I want to take you on a journey. Because this is not just a physics lesson. This is the story of humanity. The story of how we, a species of clever primates on a tiny rocky planet, orbiting an ordinary star in an unremarkable galaxy, slowly, painfully, beautifully, came to understand our place in the cosmos, or rather, came to understand that we do not have a special place in the cosmos. And that journey, that slow stripping away of our cosmic ego, is one of the most profound stories ever told. It spans thousands of years. It involves geniuses and heretics, telescopes and equations, pigeon droppings and Nobel Prizes. And it leads to a conclusion that is simultaneously humbling and liberating, terrifying and beautiful. So settle in, get comfortable, because this is going to be a long ride. And I promise you, by the end of it, you will never look at the night sky the same way again. Today, we are going to start with ancient humans staring up at the sky, convinced that they were the center of everything. We are going to travel through the Copernican revolution, through Galileo's telescope, through Einstein's equations, through the discovery of the expanding universe, through the cosmic microwave background, through inflation theory, through dark energy, through the geometry and topology of spacetime itself. We are going to debunk every misconception you have ever had about the Big Bang. We are going to explore what expansion really means, We are going to wrestle with questions that sit at the boundary of physics and philosophy. And we are going to arrive at a truth so strange, so counterintuitive, and so beautiful that it will change you. I am not exaggerating. This is one of those ideas that, once you truly understand it, you cannot ununderstand it. It becomes part of how you see reality. So let us begin. Imagine you are a human being living 10,000 years ago. You have no telescope. You have no mathematics beyond basic counting. You have no concept of atoms or light years or galaxies. All you have are your eyes, your curiosity, and the sky above you. And what do you see when you look up? You see the sun rise in the east and set in the west. You see the moon do roughly the same thing. You see the stars appear at night and wheel slowly across the sky in great circular arcs, as if they are painted on the inside of a giant rotating dome. And if you watch carefully, night after night, month after month, you notice that the stars rotate around a single point. In the northern hemisphere, that point is roughly where Polaris, the North Star, sits. Everything seems to revolve around you. The sun serves you with warmth and light. The moon illuminates your nights. The stars provide a backdrop to your existence. You are, as far as you can tell, at the absolute center of everything. And this is not arrogance. This is observation. This is what the sky actually looks like from the surface of Earth. If you had no other information, no other tools, no other framework, you would conclude exactly what ancient humans concluded. Earth is the center. Everything revolves around Earth. We are the most important thing in the cosmos. This idea, this geocentric model, was not just some casual belief. It was formalized, mathematized, and elevated to the status of absolute truth. The ancient Greeks, brilliant as they were, built an entire cosmology around it. Aristotle, one of the greatest thinkers in human history, argued that Earth must be at the center because heavy things fall toward the center of the universe, and since heavy things fall toward Earth, Earth must be at the center. It sounds circular when I say it like that, and it is, but at the time it was considered airtight logic. And then came Claudius Ptolemy, an astronomer working in Alexandria around 150 AD, who created the most detailed and sophisticated geocentric model the world had ever seen. His great work, the Almagest, described a universe in which the sun, the moon, the planets, and the stars all orbited Earth in complex patterns of circles upon circles, called epicycles. The planets did not just go around Earth in simple circles. They went around in small circles that themselves traveled around in larger circles. It was complicated. It was elaborate. It was in a way beautiful. And most importantly, it worked. Ptolemy's model could predict where planets would be in the sky with reasonable accuracy. It could predict eclipses. It could be used for navigation. And because it worked, people believed it. Not just for a few decades, not just for a few centuries. For nearly 1,400 years, Ptolemy's geocentric model was the accepted model of the universe. Think about that. For 1,400 years, the entirety of Western civilization and much of the rest of the world believed that Earth sat motionless at the center of everything, that the cosmos literally revolved around us, that we were, by the design of God or nature or whatever you want to call it, the most important thing in existence. And there is a reason this belief lasted so long, a reason beyond just the science. It felt right. It felt correct in a way that went deeper than mathematics or observation. It resonated with something fundamental in the human psyche. We want to be special. We want to matter. We want the universe to care about us, to be organized around us, to have us at its heart. This is not a flaw in human thinking. It is a feature. It is how evolution shaped us. A creature that believes it is important, that believes its survival matters, is more likely to fight for that survival. The ego is a survival tool, but it is also a lens, and like all lenses, it can distort. And the distortion it created in our understanding of the cosmos lasted for millennia, because every time someone suggested that maybe, just maybe, Earth was not at the center, they were not just challenging a scientific model. They were challenging the very idea that humans are special. And people do not take kindly to having their specialness questioned. But the truth does not care about our feelings, and the truth was coming. It came in the form of a quiet, cautious, deeply religious Polish mathematician named Nicolaus Copernicus. And what Copernicus did was so revolutionary, so dangerous, so fundamentally world-altering that he was afraid to do it. He developed his heliocentric model, his sun-centered model, over decades of careful work. He showed that if you put the sun at the center instead of Earth, the motions of the planets became simpler. The epicycles mostly disappeared. The retrograde motion of the planets, that weird backward loop they seem to make in the sky, was explained naturally as a consequence of Earth overtaking slower outer planets in their orbits. The math was cleaner, the model was more elegant, and Copernicus knew it was right. But he also knew what it meant. It meant Earth was not the center. It meant we were not special. It meant the entire philosophical and theological framework of Western civilization was built on a lie. And so he did something that tells you everything you need to know about the courage it takes to tell an uncomfortable truth. He waited. He waited until he was literally on his deathbed in 1543 to publish his masterwork, De Revolutionibus Orbium Coelestium. Legend has it that a copy of the printed book was placed in his hands on the very day he died. He never had to face the consequences, but others would. Before I continue with what happened next, I want to pause here and ask you something. If you are watching this wherever you are in the world, I want to know where you are watching from. Drop it in the comments right now. Are you watching from India, Pakistan, Bangladesh, the United States, the United Kingdom, Germany, Saudi Arabia, Australia? Wherever you are, let me know. Because what I love about science is that it is universal. It does not belong to any one country or culture or language. The universe has no center, and neither does knowledge. It belongs to everyone, everywhere. So tell me where you are, and while you're at it, if you are enjoying this deep dive into the cosmos, hit that like button. It helps more people find this video. And trust me, what is coming next is going to blow your mind even more. Because Copernicus was just the beginning. After Copernicus, the next act in this cosmic drama belonged to a man who had something Copernicus did not: a telescope. Galileo Galilei, the father of observational astronomy, turned his crude but revolutionary telescope toward the sky in 1609 and 1610, and what he saw demolished the geocentric model in ways that could not be ignored. First, he looked at Jupiter and discovered 4 moons orbiting it. This was devastating to the geocentric model because it proved that not everything in the cosmos orbits Earth. Here were 4 objects, clearly visible through the telescope, going around Jupiter. If everything was supposed to orbit Earth, what were these moons doing orbiting Jupiter? Second, Galileo observed the phases of Venus. He saw Venus go through a full set of phases just like the moon, from a thin crescent to a full disk. This was only possible if Venus orbited the Sun, not Earth. In Ptolemy's geocentric model, Venus could never appear as a full disk as seen from Earth. The telescope showed otherwise. Third, he observed the surface of the moon and saw mountains, craters, and valleys. This shattered the Aristotelian idea that celestial bodies were perfect, unblemished spheres. The moon was a world with geography, not a divine light. And Galileo, unlike Copernicus, was not quiet about it. He published, he argued, he debated, he proclaimed the truth loudly and publicly, and the truth, as it so often does, got him in trouble. The Catholic Church, which had adopted the geocentric model as a matter of religious doctrine, put Galileo on trial. In 1633, he was found guilty of heresy, forced to recant his belief that Earth moves around the Sun, and sentenced to house arrest for the remainder of his life. Legend says that as he left the courtroom, he muttered under his breath, "Eppur si muove," and yet it moves. Whether he actually said it or not, the sentiment is perfect. You can silence a man. You can lock him up. You can make him say the words you want him to say, but you cannot stop the Earth from orbiting the Sun. The truth does not care about your authority. It simply is. And now, with the geocentric model crumbling, a new question emerged. If Earth is not the center of the universe, then what is? The initial answer seemed obvious: the Sun. Copernicus had placed the Sun at the center, and for a while that seemed like the correct answer. We went from a geocentric universe to a heliocentric universe. The Sun was the king. The Sun was the center. Everything orbited the Sun. Except that was not quite right either. Johannes Kepler, working with the exquisitely precise observational data of Tycho Brahe, discovered that the planets do not orbit the Sun in perfect circles. They orbit in ellipses. And the Sun is not even at the center of these ellipses. It is at one of the two focus points. This was a subtle but profound hint. The Sun was not even at the geometric center of the orbits of its own planets. And beyond Kepler's orbits, there was an even bigger problem with calling the Sun the center of the universe, because the Sun, as it would later be discovered, is just one star among many, and many does not even begin to describe it. Let us jump forward in time to the early 20th century, because this is where the story accelerates dramatically. By this point, astronomers had telescopes powerful enough to see far beyond our solar system. They could see thousands, millions of stars, and they could see strange fuzzy patches of light scattered across the sky, which they called nebulae, from the Latin word for cloud. The question was, what were these nebulae? Were they clouds of gas within our own galaxy, or were they something else entirely? This question led to what is known as the Great Debate of 1920, one of the most important scientific debates in history. On one side was Harlow Shapley, who argued that the Milky Way was essentially the entire universe. Those fuzzy nebulae were just gas clouds within our galaxy. On the other side was Heber Curtis, who argued that at least some of those nebulae were actually separate galaxies, what he called island universes, far beyond the Milky Way. The debate was intense, and it could not be settled by argument alone. It needed evidence. And that evidence came from a man sitting at a telescope on a mountain in California. Edwin Hubble working at the Mount Wilson Observatory, did something in 1924 that changed the course of human history. Using the 100-inch Hooker telescope, the most powerful telescope in the world at the time, he observed a type of star called a Cepheid variable in the Andromeda Nebula. Cepheid variables are special because they pulsate with a period that is directly related to their intrinsic brightness. By measuring the period of pulsation, you can figure out how bright the star actually is. By comparing that to how bright it appears, you can calculate how far away it is. Hubble did this calculation for the Cepheid in Andromeda, and the answer was staggering. Andromeda was not inside the Milky Way. It was roughly 1 million light-years away. It was far, far beyond the boundaries of our galaxy. It was, in fact, a separate galaxy. An entirely separate island of hundreds of billions of stars comparable in size to our own Milky Way. Curtis was right. The Milky Way was not the whole universe. It was just one galaxy among, as we now know, hundreds of billions, perhaps trillions of galaxies. And just like that, the Sun lost any remaining claim to being the center of the universe. Our Sun was not even at the center of the Milky Way. Shapley himself had shown that. Using observations of globular clusters, those dense spherical collections of ancient stars that orbit the Milky Way, Shapley had determined that the Sun lies roughly 26,000 light-years from the galactic center. We are not in the middle of our own galaxy. We are out in the suburbs, in one of the spiral arms, orbiting the galactic center along with hundreds of billions of other stars. If the Milky Way were a city, we would not be in the town square. We would be in a quiet neighborhood on the outskirts, and the Milky Way itself is just one galaxy among trillions. So the center of the Milky Way is not the center of the universe either. Do you see the pattern here? Every single time humanity has identified something as the center of the universe, we have been wrong. Earth was the center, wrong. The Sun was the center, wrong. The Milky Way was the whole universe, wrong. The center of the Milky Way was the center, wrong. And this pattern is not a coincidence. It is a clue. It is the universe trying to tell us something profound. There is no center. But to really understand why, we need to go deeper, much deeper, because Hubble was not done. In addition to discovering that the universe contained many galaxies far beyond our own, Hubble made a second discovery that was even more revolutionary. He noticed that the light from distant galaxies was shifted toward the red end of the spectrum. This is called redshift, and it is analogous to the Doppler effect for sound. When an ambulance drives toward you, its siren sounds higher pitched because the sound waves are compressed. When it drives away, the siren sounds lower pitched because the sound waves are stretched out. Light works the same way. When a galaxy moves away from us, its light waves are stretched, shifting toward the red end of the spectrum. When a galaxy moves toward us, its light waves are compressed, shifting toward the blue end. And what Hubble found was that almost every galaxy he observed was redshifted. They were all moving away from us. But that was not the really shocking part. The really shocking part was the relationship between a galaxy's distance and its speed. The farther away a galaxy was, the faster it was moving away from us. This relationship, now known as Hubble's law, is expressed as a simple equation. The velocity of recession equals the Hubble constant times the distance. V equals h naught times d. And this equation contains within it one of the most profound insights in the history of human thought. If everything is moving away from everything else, and if the farther things are, the faster they are moving apart, then if you reverse the clock, if you run the movie backward, everything was once closer together. Go back far enough, and everything was much, much closer. Go back far enough, and all the matter and energy in the entire observable universe was compressed into an unimaginably small, unimaginably hot, unimaginably dense state. This is what we call the Big Bang. And this is exactly where most people go wrong. Most people, when they hear about the Big Bang, imagine an explosion. They imagine a tiny point of matter and energy floating in some pre-existing empty space that suddenly exploded outward, sending matter and energy flying in all directions, like a grenade going off, like a firecracker, like a bomb. And in this mental image, the center of the explosion is obvious. It is the point where the grenade was, the point from which everything flew outward, the original location, the source. And this mental image is completely, totally, utterly, fundamentally wrong, and understanding why it is wrong is the key to understanding why the universe has no center. The Big Bang was not an explosion in space. Let me say that again, because it might be the most important sentence in this entire video. The Big Bang was not an explosion in space. The Big Bang was an expansion of space. Those two things sound similar, but they are radically different. An explosion in space means that something blew up at a particular location within a pre-existing space, and debris flew outward into the surrounding emptiness. That is not what happened. There was no pre-existing space. There was no surrounding emptiness. There was no particular location. What happened was that space itself came into existence and began expanding. Space itself was born. Time itself was born. The Big Bang did not happen at a particular point in space because space did not exist before the Big Bang. The Big Bang did not happen at a particular moment in a pre-existing timeline because time did not exist before the Big Bang. There was no before. There was no where. There was only the event itself, the sudden coming into existence of space and time and matter and energy all at once, everywhere, simultaneously. The singularity that preceded the Big Bang, if we can even use the word preceded when talking about the birth of time, was not a point in space. It was all of space. All of space was compressed into that singularity. Not a tiny region of space, all of it. The entire universe, infinite or finite, whatever it is, was the singularity. And when the Big Bang happened, it was not matter flying outward from a point. It was space itself expanding everywhere, all at once, equally, uniformly. The Big Bang happened here, and it happened there, and it happened everywhere. It happened where you are sitting right now. It happened at the farthest star you can see. It happened at the most distant galaxy ever observed. It happened everywhere, because everywhere is where it happened. I know this is hard to wrap your head around. It is one of the most counterintuitive ideas in all of science. So let me give you some analogies that might help. The most famous one is the balloon analogy. Imagine the surface of a balloon, not the inside of the balloon, not the air inside, not the three-dimensional volume, just the surface, the two-dimensional surface. Now imagine that this surface is the entire universe, and the creatures living in this universe are two-dimensional beings who can only move along the surface. They have no concept of inward or outward, because those directions do not exist in their two-dimensional reality. Now, take a marker and draw some dots on the surface of the balloon. These dots represent galaxies. Now, blow up the balloon. What happens? As the balloon inflates, the surface stretches. The dots move apart from each other. Every dot moves away from every other dot. A dot on one side of the balloon sees dots on the other side moving away from it. But here is the critical question. Where is the center of this expansion on the surface? There is no center on the surface. No dot is the center. Every dot sees every other dot moving away from it. Every dot, from its own perspective, appears to be at the center of the expansion. But no dot actually is the center. The center of the balloon, the geometric center of the sphere, is not on the surface. It is inside the balloon in a direction that the two-dimensional creatures on the surface cannot access. It is in a third dimension that they cannot perceive. Now, translate this to our universe. We are like those two-dimensional creatures, except we are three-dimensional. We live in a three-dimensional space that is expanding, just like the two-dimensional surface of the balloon. And the center of this expansion, if it exists at all, is not in any direction we can point to. It is not north or south, east or west, up or down. It might be in a fourth spatial dimension, a dimension we cannot perceive, cannot access, cannot even point toward, or it might not exist at all. On the surface of the balloon, there is no center, period. And in our three-dimensional expanding universe, there is no center, period. Let me give you another analogy that some people find even more helpful. Imagine you are baking raisin bread. You have a ball of dough with raisins scattered throughout it. Now you put the dough in the oven and it begins to rise. The dough expands. As it expands, every raisin moves away from every other raisin. Pick any raisin at all, and from its perspective, every other raisin is moving away from it. And the farther away a raisin is, the faster it is moving away. Sound familiar? That is exactly what Hubble observed. Every galaxy is moving away from every other galaxy, and the farther apart they are, the faster they are receding. Now, in the raisin bread analogy, is any raisin at the center of the expansion? No. Every raisin sees itself as the center, but no raisin is special. The expansion is happening everywhere equally, throughout the entire loaf. There is no center of the rising, no point from which the expansion originates. The expansion is a property of the dough itself, not a property of any particular location within the dough. And this is exactly how the expansion of the universe works. It is not an expansion from a center. It is an expansion of space itself, happening everywhere equally, simultaneously. But analogies can only take us so far. They are useful mental tools, but they are imperfect. The balloon analogy, for instance, has a major flaw. The surface of a balloon is a two-dimensional curved surface embedded in three-dimensional space. This might lead you to think that our three-dimensional universe is embedded in four-dimensional space, and that the center of the universe is out there somewhere in the fourth dimension. That is a possible interpretation, but it is not necessarily correct. The mathematics of general relativity does not require our universe to be embedded in a higher dimensional space. Our three-dimensional universe can be curved, can be expanding, can have all of these properties without needing to exist within a higher dimensional container. It is like the difference between intrinsic curvature and extrinsic curvature. The curvature of the universe is intrinsic. It can be measured and described entirely from within, without reference to any higher dimension. So the center might not just be inaccessible to us, it might not exist at all. Not in our dimensions, not in higher dimensions, nowhere. The raisin bread analogy has its own flaw. A loaf of bread has edges. It has a finite size. You can, in principle, find the center of the loaf. But the universe, as far as we know, has no edges. It might be infinite, stretching forever in all directions. Or it might be finite but unbounded, like the surface of a sphere, where you can walk forever without ever reaching an edge. In either case, there is no boundary, and without a boundary, the concept of a center becomes meaningless. How do you find the center of something that has no edges? You cannot. It is like asking what is north of the North Pole. The question itself is flawed. It assumes a framework that does not apply. This brings us to one of the most important ideas in modern cosmology, an idea so fundamental that it underpins almost everything we know about the universe on the largest scales. It is called the cosmological principle, and it says, in essence, that the universe, when viewed on sufficiently large scales, looks the same everywhere and in every direction. The technical terms are homogeneous and isotropic. Homogeneous means that the properties of the universe are the same at every point. The density of matter, the rate of expansion, the laws of physics, everything is the same whether you are here or 1 billion light years from here or 10 billion light years from here. Isotropic means that the universe looks the same in every direction. If you stand at any point in the universe and look around, you see the same thing no matter which way you look. The same density of galaxies, the same rate of expansion, the same background radiation. Now think about what this means for the question of a center. If the universe is homogeneous, if every point is the same as every other point, then no point is special. No point is different. No point can be distinguished as the center, because there is nothing that makes it different from any other point. If the universe is isotropic, if it looks the same in every direction from every point, then there is no preferred direction, no arrow pointing toward a center, no way to orient yourself toward the middle. The cosmological principle essentially says that asking where is the center of the universe is like asking which point on a perfectly uniform, featureless, infinite plane is the center. The question has no answer because every point is identical to every other point. And the cosmological principle is not just an assumption. It is supported by overwhelming observational evidence. The most powerful piece of evidence is the cosmic microwave background radiation, often abbreviated as CMB. And the story of its discovery is one of the most delightful accidents in the history of science. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, using a large horn-shaped antenna originally designed for satellite communications. They were trying to detect very faint radio signals, but they kept picking up a persistent, annoying hiss of static, a background noise that they could not get rid of no matter what they did. They pointed the antenna in different directions. The noise was the same everywhere. They checked for equipment malfunction. Nothing wrong. They even found that pigeons had been nesting inside the antenna and cleaned out the pigeon droppings, thinking that might be causing the interference. It was not the pigeons. The noise persisted. It came from every direction in the sky. It had no source. It had no variation. It was just there, everywhere, constant and unchanging. What Penzias and Wilson had accidentally discovered was the cosmic microwave background, the afterglow of the Big Bang, the oldest light in the universe. Here is what the CMB is. About 380,000 years after the Big Bang, the universe had cooled down enough for atoms to form. Before that, the universe was so hot that electrons could not bind to nuclei. The whole universe was a seething plasma of charged particles, and because charged particles scatter light, the universe was opaque. Light could not travel freely. It was like being inside a thick fog. But when the universe cooled enough for atoms to form, suddenly the fog lifted. Light was free to travel. And the light that was released at that moment, the light from the moment the universe became transparent, has been traveling through space ever since. For 13.8 billion years, this light has been streaming through the cosmos, stretched by the expansion of space from its original visible wavelengths into microwave wavelengths. This is what Penzias and Wilson detected. This is the CMB. It is literally the baby picture of the universe, a snapshot of what the cosmos looked like when it was only 380,000 years old. And here's why the CMB is so important for our question about the center of the universe. The CMB is almost perfectly uniform. Its temperature is 2.725 Kelvin everywhere, in every direction. The variations are tiny, about 1 part in 100,000. This means that the universe, at the time the CMB was released, was almost perfectly uniform in density and temperature. It was the same everywhere, and that uniformity has a crucial implication. If the universe had a center, if the Big Bang had happened at a particular point and matter had exploded outward from that point, then we would expect the CMB to look different in different directions. We would expect more radiation from the direction of the center and less radiation from the direction of the edge. We would expect a gradient, a pattern, and a symmetry. But we see no such thing. The CMB is the same in every direction to an astonishing degree of precision. This is direct, observable, measurable evidence that the universe has no center. Later observations by satellites like COBE, WMAP, and Planck have mapped the CMB in exquisite detail, measuring those tiny 1 in 100,000 fluctuations with incredible precision. These fluctuations are the seeds from which all the structure in the universe grew, the galaxies, the galaxy clusters, the great cosmic web. And the pattern of these fluctuations matches perfectly with a universe that is homogeneous and isotropic. A universe with no center. A universe where every point is equivalent to every other point. The data is clear. The evidence is overwhelming. The CMB is telling us in no uncertain terms that the universe does not have a preferred location. It does not have a center. Now, I want to address something that might be confusing you. You might be thinking, wait a minute, you just said we can see the CMB in every direction around us. That means we are looking out at a sphere of ancient light, with us at the center. Does not that make us the center? This is a really important point, so let me be very clear. Yes, we are at the center of our observable universe, but that is not the same thing as being at the center of the universe. The observable universe is the region of space from which light has had time to reach us since the Big Bang. Because the universe is 13.8 billion years old, there is a limit to how far we can see. The edge of our observable universe is about 46.5 billion light-years away in every direction. Why 46.5 and not 13.8? Because the universe has been expanding this whole time, so the objects that emitted the light we see from the early universe have since moved much farther away. The observable universe is a sphere centered on us, yes. But this is not because we are at the center of the universe. It is simply because we are the observer. Every observer, anywhere in the universe, has their own observable universe centered on them. An alien on a planet in a galaxy 10 billion light years away has its own observable universe, a sphere centered on that alien extending 46.5 billion light years in every direction from that alien. And that alien's observable universe overlaps with ours in some regions and extends beyond ours in others. There is nothing special about our position. We are at the center of our observable universe in the same way that you are at the center of your visual horizon. When you stand in an open field, you can see to the horizon in every direction. You appear to be at the center of a circle defined by the horizon. But this does not mean you are at the center of the field. It just means you have limited vision. If you walk a mile in any direction, you will have a new horizon, a new circle, with you still at the center. But the field has not changed. You have just moved your viewpoint. The observable universe is our cosmic horizon. We are at the center of our horizon, but the universe itself has no center. I want to pause here for a moment, because if you have followed everything so far, you have already absorbed one of the most profound ideas in cosmology. You understand that the Big Bang was not an explosion at a point. You understand that space itself is expanding. You understand that there is no center to this expansion. You understand that the CMB confirms the uniformity of the universe. And you understand the difference between the observable universe and the universe itself. That is an enormous amount of deep physics. And I want to know right now in the comments, where are you watching this from? And has this video changed the way you think about the cosmos? Tell me. Because we are about to go even deeper. And if you have not already subscribed, now is the time. Hit that subscribe button and the bell icon so you never miss a deep dive like this. Because what I am about to explain next, the expansion of space, the faster-than-light recession, the geometry and shape of the universe, this is where things get truly mind-bending. Let us talk about what it really means for space to be expanding. Because I have used that phrase multiple times now, and I want to make sure you genuinely understand it, because it is one of the most counterintuitive ideas in all of physics. When I say the universe is expanding, most people picture galaxies flying through space, moving apart like shrapnel from an explosion. But that is not what is happening. The galaxies are not moving through space. Space itself is getting bigger. The space between the galaxies is growing. Imagine taking a rubber sheet and drawing dots on it. The dots represent galaxies. Now stretch the rubber sheet, pull it in all directions, uniformly. What happens? The dots move apart. But the dots did not move on the rubber sheet. The rubber sheet itself expanded. The dots are in the same positions on the sheet, but the sheet is bigger now. So the distances between the dots have increased. This is what is happening with the real universe. Galaxies are not flying through space away from each other. They are sitting in space, and space itself is stretching. The amount of space between them is increasing. This is called metric expansion, and it is fundamentally different from motion through space. And this distinction leads to one of the most mind-blowing consequences in all of cosmology. The rate of expansion is described by the Hubble constant. Currently, the best measurements put it at roughly 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. So for every 3.26 million light years of distance between two objects, the space between them is expanding at an additional 70 kilometers per second. For nearby galaxies, this is a small effect. The Andromeda Galaxy is only about 2.5 million light years away, and it is actually moving toward us under the influence of gravity, which overwhelms the expansion at such short distances. But for distant galaxies, the expansion adds up. A galaxy 1 billion light-years away is receding at about 21,000 kilometers per second. A galaxy 5 billion light-years away is receding at about 105,000 kilometers per second. And a galaxy far enough away, it is receding faster than the speed of light. Yes, you heard that correctly. There are galaxies in the universe that are moving away from us faster than light. And no, this does not violate Einstein's theory of relativity. Einstein said that nothing can travel through space faster than light. And that is true. No object can move through space faster than 300,000 kilometers per second. But the galaxies are not moving through space faster than light. The space between us and those galaxies is expanding so rapidly that the total rate of separation exceeds the speed of light. This is allowed by relativity because it is not motion through space. It is the expansion of space itself. And there is no speed limit on the expansion of space. This has a profound consequence. It means there are regions of the universe that we can never see, never communicate with, and never interact with. Light from those regions will never reach us, because the space between us is expanding faster than the light can travel. These regions are beyond our cosmic horizon, forever out of reach. And this is true for every observer in the universe. Every observer has regions beyond their horizon. No observer can see everything. And this means that asking, where is the center of the universe, is even more hopeless than it might seem, because no one, nowhere, can even see the whole universe to determine where a center might be. We are all limited to our own patch, our own observable bubble, and from within that bubble, everything looks the same in every direction. Every bubble looks the same. No bubble is special. No bubble is the center. Now let us talk about the shape of the universe, because this is crucial to understanding why there is no center. When cosmologists talk about the shape of the universe, they are not talking about its outward appearance, like whether it looks like a ball or a cube. They are talking about its geometry, the rules that govern how space is curved on the largest scales. And there are essentially three possibilities. The first possibility is that the universe has positive curvature, like the surface of a sphere. In this case, if you travel in a straight line far enough, you will eventually come back to where you started, just like circumnavigating the Earth. Parallel lines will eventually converge. The angles of a triangle will add up to more than 180 degrees. And the universe would be finite in volume, but have no boundaries, no edges, just like the surface of a sphere is finite in area, but has no edges. The second possibility is that the universe has negative curvature, like a saddle or a Pringle chip. In this case, the universe extends forever, parallel lines diverge, and the angles of a triangle add up to less than 180 degrees. The third possibility is that the universe is flat, perfectly, exactly, precisely flat. Euclidean geometry works on the largest scales. parallel lines stay parallel forever. The angles of a triangle add up to exactly 180 degrees. And the universe might extend forever, or it might have some exotic finite topology. But its curvature is zero. So which is it? How do we measure the shape of the universe? One way is to use the CMB. The tiny fluctuations in the CMB have a characteristic size, and this size appears larger or smaller depending on the curvature of the universe. In a positively curved universe, the fluctuations would appear bigger than expected. In a negatively curved universe, they would appear smaller. In a flat universe, they would appear at exactly the predicted size. The WMOP and Planck satellites measured these fluctuations with incredible precision. And the result? The universe is flat, or so breathtakingly close to flat that we cannot distinguish it from perfectly flat with our current instruments. The curvature, if it exists, is so small as to be negligible. The universe appears to be flat to within the precision of our best measurements. This result is remarkable and somewhat mysterious, and we will come back to why later when we talk about inflation. But for now, let us focus on what it means for the center question. If the universe is flat and infinite, then it has no center by definition. How do you find the center of an infinite plane? You cannot. It extends forever in every direction. There is no boundary, no edge, no outermost point from which you could measure inward to find a midpoint. Every point on an infinite plane is exactly equivalent to every other point. None is the center. None is the edge. None is special. If the universe is flat and finite, it could have a topology like a torus, a donut shape in higher dimensions, where traveling far enough in one direction brings you back to your starting point. Even on the surface of a torus, there is no center. Just like on the surface of a sphere, every point is equivalent. If the universe has positive curvature and is like the surface of a sphere in higher dimensions, then again, there is no center on the surface. The center of a sphere is in the interior, in a dimension that surface dwellers cannot access. And the universe's surface is all there is. There is no interior in a higher dimension that we can point to. In every possible case, whether the universe is flat or curved, infinite or finite, open or closed, there is no center. The mathematics is unambiguous. The geometry does not allow for a center. It is not that we have not found the center, it is that the concept of a center is incompatible with the geometry of the universe as we understand it. Let me introduce Einstein more formally into this story, because his ideas are the mathematical backbone of everything I have been telling you. In 1915, Albert Einstein published his general theory of relativity, one of the most beautiful and successful theories in the history of physics. General relativity describes gravity not as a force, as Newton had, but as a curvature of space-time. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. This is one of the most elegant ideas ever conceived by a human mind. It replaced the concept of gravity as a mysterious force acting at a distance with a geometric description of reality itself. In general relativity, the trajectory of a planet around a star is not the result of a gravitational force pulling on the planet. It is the result of the planet following the straightest possible path, a geodesic, through the curved space-time created by the star's mass. The planet is not being pulled, it is moving in a straight line through curved space. And this framework, this description of gravity as geometry, is what allows us to talk about the shape and curvature of the universe as a whole. When Einstein first applied his equations to the universe as a whole, he assumed that the universe was static, neither expanding nor contracting. This was the prevailing view at the time, and it was consistent with the observed sky, which appeared unchanging on the largest scales. But Einstein's equations did not naturally produce a static universe. They predicted that the universe should be either expanding or contracting. So Einstein introduced a fudge factor, a term he called the cosmological constant, represented by the Greek letter lambda, to counteract the tendency of the universe to expand or contract and keep it static. He essentially added a repulsive force to balance gravity, creating a static solution. In 1922, a Russian mathematician named Alexander Friedmann took Einstein's equations and solved them without the cosmological constant. He found that the equations naturally predicted an expanding or contracting universe. 3 possible solutions emerged depending on the density of the universe relative to a critical value. If the density is above the critical value, the universe expands, slows down, stops, and contracts, a closed universe heading for a big crunch. If the density is below the critical value, the universe expands forever, with the expansion slowing but never stopping, an open universe. If the density equals exactly the critical value, the universe expands forever, but the expansion rate asymptotically approaches 0, a flat universe on the knife edge between the other two. All 3 of Friedmann's solutions describe a universe that is homogeneous and isotropic. All 3 describe a universe with no center. The mathematics of general relativity, in all its solutions, does not produce a center. It produces a universe that looks the same everywhere and in every direction. This is not someone's opinion. This is not a philosophical stance. This is what the equations say. A few years after Friedmann, in 1927, a Belgian physicist and Catholic priest named Georges Lemaitre independently derived the same expanding universe solutions from Einstein's equations. He went even further, proposing that if the universe is expanding, then in the past it must have been smaller, denser, and hotter. Running the clock backward, he suggested, would lead to a primeval atom, a single point of origin from which the entire universe expanded. This was the first articulation of what we now call the Big Bang theory. And when Hubble's observations confirmed the expansion in 1929, the theoretical picture and the observational evidence came together in a perfect convergence of truth. Einstein, upon learning of Hubble's observations and the work of Friedmann and Lemaitre, reportedly called his introduction of the cosmological constant his biggest blunder. He had had the chance to predict the expansion of the universe before it was observed, but he had instead introduced an ad hoc term to prevent his equations from telling him what they were trying to tell him. The universe is expanding. There is no static balance. There is no fixed center around which things are arranged. There is only expansion everywhere, equally, from every point. But here is an irony so delicious that the universe itself might appreciate it. The cosmological constant that Einstein introduced and then regretted, it came back. In 1998, 2 teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were studying a particular type of exploding star called a Type 1a supernova. Type 1a supernova are useful because they all explode with roughly the same intrinsic brightness, making them excellent standard candles for measuring cosmic distances. By observing how bright a Type 1a supernova appears from Earth and comparing that to how bright it actually is, you can calculate how far away it is. The two teams were using this technique to measure how the expansion of the universe was changing over time. The expectation was that the expansion would be slowing down. Gravity, the mutual attraction of all the matter in the universe, should be pulling everything together, decelerating the expansion. Think of it like throwing a ball upward. Gravity pulls it back, slowing it down. The ball decelerates. Everyone expected the cosmic expansion to be decelerating in the same way. But what the two teams found was the exact opposite. The expansion was not slowing down. It was speeding up. The universe was not decelerating, it was accelerating. Distant supernovae were dimmer than expected, meaning they were farther away than they should be if the expansion were slowing. The universe was expanding faster and faster. This was one of the most shocking discoveries in the history of science. It was so unexpected that the teams checked and rechecked their data obsessively before publishing. But the result held up, and it demanded an explanation. What force or energy could be pushing the universe apart, counteracting gravity, causing the expansion to accelerate? The answer, or rather the placeholder for the answer, was given the name dark energy. And here is where Einstein's biggest blunder makes its triumphant return. The simplest mathematical description of dark energy is, you guessed it, the cosmological constant, lambda. The very term Einstein introduced to keep the universe static turns out to be real, but instead of preventing expansion, it is driving acceleration. Dark energy makes up approximately 68% of the total energy content of the universe. It is the dominant component. More than ordinary matter, more than dark matter, more than radiation. And we have essentially no idea what it is. We know its effects. We can measure it. We can describe it mathematically. But its fundamental nature remains one of the deepest mysteries in physics. It could be the energy of empty space itself, the quantum vacuum energy. It could be a dynamic field that changes over time, sometimes called quintessence. It could be something else entirely that we have not even imagined yet. But whatever dark energy is, it has a crucial property relevant to our question. It is uniform. It has the same density everywhere in the universe. It does not clump. It does not concentrate. It does not form structures. It is the same here, there, and everywhere. And because it drives the expansion of the universe equally from every point, it reinforces the fundamental message. There is no center. The acceleration is the same everywhere. No point is expanding faster or slower than any other point. The universe is accelerating uniformly, without a center, without an edge, without a preferred location. And the implications of this accelerating expansion for the far future are both fascinating and haunting. If dark energy continues to drive acceleration, as current observations suggest it will, then the universe will expand forever. The expansion will never stop, never reverse, never lead to a big crunch. Instead, the universe faces what cosmologists call the heat death, also known as the Big Freeze. Over trillions of years, the expansion will cause galaxies to move so far apart that the light from one galaxy can never reach another. Each galaxy will become an isolated island in an ever-growing void of empty space. Stars will burn out. Black holes will evaporate through Hawking radiation over incomprehensible timescales. The universe will approach a state of maximum entropy, a state of perfect uniformity and perfect coldness, where nothing interesting can ever happen again. And here is the haunting part. Trillions of years from now, if intelligent beings exist in some far future galaxy, they will look out at their sky and see nothing, just their own galaxy, alone in a vast, empty darkness. The other galaxies will have moved beyond their cosmic horizon. The CMB will have been stretched to undetectable wavelengths. They will have no evidence that the Big Bang ever happened, no evidence that other galaxies ever existed. They will think their galaxy is the entire universe. They will make the same mistake we made 100 years ago. The universe will have expanded so much that the evidence of its own expansion will have been erased. They will believe they are at the center of a small static cosmos. And they will be wrong, just like we were wrong, but they will have no way of knowing it. Now let me take you into the very first fraction of a second after the Big Bang, because there is a period of time so brief, so violent, and so transformative that it deserves its own deep exploration. It is called cosmic inflation, and it might be the ultimate reason why the universe has no center, or at least why any trace of a center, if one ever existed, was utterly obliterated. In the early 1980s, a physicist named Alan Guth was working on problems in particle physics when he stumbled upon an idea that would revolutionize cosmology. He was trying to understand why the universe has certain properties that the standard Big Bang model could not explain. There were three main puzzles. The first was the horizon problem. The CMB is the same temperature in every direction to 1 part in 100,000. But regions on opposite sides of the sky are so far apart that light has not had time to travel between them since the Big Bang. How can two regions that have never been in causal contact, that have never had the chance to exchange energy or information, be at exactly the same temperature? It is like finding two people on opposite sides of the planet wearing the exact same outfit. If they have never communicated, the coincidence is staggering. The second puzzle was the flatness problem. As I mentioned earlier, the universe appears to be flat to incredible precision. But here is the thing. A flat universe is unstable. If the universe were even slightly curved at the time of the Big Bang, that curvature would have been amplified over time. For the universe to be as flat as we observe it today, 13.8 billion years after the Big Bang, it must have been unimaginably flat at the beginning. The density of the universe at 1 second after the Big Bang must have been equal to the critical density to within 1 part in 1,000 trillion. That level of fine-tuning demands an explanation. The third puzzle was the magnetic monopole problem. Certain theories of particle physics predict that the early universe should have produced vast numbers of magnetic monopoles, hypothetical particles with only a north or south magnetic pole, not both. But we have never detected a single magnetic monopole. Where did they all go? Guth's solution to all three problems was breathtakingly elegant. He proposed that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion so rapid that it makes the current expansion look like a lazy stroll. During this inflationary period, which lasted from roughly 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds after the Big Bang, the universe doubled in size at least 60 to 80 times. Think about what that means. Doubling once makes something twice as big. Doubling it 60 times makes it about a quintillion times bigger. A region of space smaller than an atom was inflated to a size larger than the entire observable universe, all in a time interval so short that light could barely travel the width of a proton. This solves the horizon problem because the regions of the sky that appear to have never been in contact actually were in contact before inflation. They were close together in the same tiny pre-inflationary patch and had time to reach a common temperature. Then inflation stretched that tiny patch to an enormous size, carrying those equalized regions far apart. They look like they have never communicated, but they did before inflation separated them. It solves the flatness problem because inflation stretches any curvature to negligible levels. Imagine the surface of a sphere. It is curved, but zoom into a tiny region of a very large sphere, and the surface looks flat. Inflation made the universe so enormous that any initial curvature was stretched to near zero, just like zooming into a tiny patch of Earth's surface makes it look flat, even though Earth is a sphere. And it solves the monopole problem because inflation diluted the monopoles to negligible density. If the universe inflated by a factor of 10 to the power of 60 or more, any magnetic monopoles produced before or during inflation would be spread out over such an enormous volume that the probability of finding one in our observable universe is essentially zero. But here is what matters most for our question about the center. Inflation did not just solve these puzzles. It obliterated any possible structure or asymmetry that might have existed before inflation. Whatever the universe looked like before inflation, whatever geometry or topology or center it might have had, inflation stretched it so dramatically that all traces were erased. It is like taking a wrinkled, lumpy, irregular ball of clay and stretching it uniformly in every direction by a factor of a quintillion. Whatever features it had are gone. It is smooth, it is flat, it is featureless. If there was a center before inflation, it was stretched to irrelevance. The entire observable universe came from a tiny, unimaginably tiny patch of the pre-inflationary universe. And that patch was homogeneous because it was in causal contact, because light had time to traverse it and equalize its properties. Inflation then took that smooth, uniform patch and blew it up to cosmic scales. The result? A universe that is smooth, uniform, and centerless, exactly as we observe. And there is an even wilder implication of inflation. The theory suggests that inflation might not have stopped everywhere at the same time. In some versions of inflation, called eternal inflation, the inflationary process is ongoing. Our region of space stopped inflating 13.8 billion years ago, and the energy of the inflationary field was converted into the hot, dense soup of particles that became our universe. But other regions might still be inflating, producing new bubble universes each time inflation stops in a local region. In this picture, our universe is just one bubble in an infinite, ever-inflating sea. There might be an infinite number of other bubble universes, each with its own Big Bang, its own expansion, its own laws of physics. This is the multiverse hypothesis, and while it remains speculative and is not yet supported by direct evidence, it is a natural consequence of many versions of inflation theory. And if the multiverse is real, then the question of the center becomes even more absurd. Where is the center of an infinite collection of bubble universes embedded in an eternally inflating space. The question has no answer. There is no center, not just of our universe, but of the entire multiverse. Centers do not exist at any level. The concept simply does not apply. Now, I want to spend some time carefully debunking the most common misconceptions about the Big Bang and the center of the universe, because even people who have a good general understanding of cosmology often harbor subtle misunderstandings. And I want to make sure that by the end of this video, you have a crystal clear understanding. The first and most common misconception is this: the Big Bang happened at a point in space, so that point is the center of the universe. This is wrong, and I have explained why in detail, but let me say it one more time in the clearest possible way. The Big Bang did not happen at a point in space. The Big Bang was the event in which space itself began to exist and expand. The singularity was not a point embedded in some larger space. The singularity was all of space compressed. When the Big Bang happened, it happened everywhere. Every point in the universe today was part of the Big Bang. The center of the Big Bang is everywhere, which means it is nowhere in particular, which means there is no center. The second misconception is this: we can see 13.8 billion years into the past in every direction, which means we are at the center. I addressed this when I talked about the observable universe, but let me reinforce it. We are at the center of our observable universe, yes. But every observer is at the center of their observable universe. This is a trivial geometric fact about spheres of observation, not a profound statement about our location. It is like saying, I am at the center of the circle of people standing around me at this party. Yes, obviously, but that does not make you the center of the party. The party has no center, or rather, every guest at the party is at the center of their own circle of nearby people. The third misconception is the universe is expanding, so it must be expanding from some central point. This confuses expansion of space with motion through space. In an explosion, debris flies outward from a center through pre-existing space. In the expansion of the universe, space itself is growing. There is no center from which the expansion originates because the expansion is happening everywhere. Go back to the raisin bread. The dough is rising everywhere. No raisin is the source of the rising. The rising is a property of the entire loaf. The fourth misconception is scientists just have not found the center yet, but someday they will. This misunderstands the nature of the claim. The claim that the universe has no center is not a statement about the limits of our current technology or the extent of our current observations. It is a consequence of the fundamental geometry and physics of the universe, the mathematics of general relativity, combined with the cosmological principle, which is supported by overwhelming observational evidence, produces a universe in which the concept of a center is undefined. It is not that we cannot find the center, it is that the center cannot exist within the framework of our best understanding of physics. Now, of course, our understanding could be wrong. Science is always provisional. But to overturn this conclusion, you would need to overthrow general relativity and the cosmological principle. And there is no evidence or theoretical reason to do so. The fifth misconception is the universe has an edge, and the center is in the middle. As far as we know, the universe does not have an edge. If it is infinite, it obviously has no edge. If it is finite, it is likely finite in the way that the surface of a sphere is finite, closed and bounded but without any edge or boundary. You can walk around the surface of a sphere forever, without ever reaching an edge. Similarly, a finite universe could wrap around on itself in higher dimensions, allowing you to travel in a straight line and eventually return to your starting point. In either case, there is no edge, no boundary, and no way to define a center. The sixth misconception is particularly subtle. If the universe came from nothing, it must have appeared somewhere. This misconception assumes that there was a pre-existing space, a stage on which the universe appeared. But the universe is not a thing that appeared on a stage. The universe is the stage. Space and time are the universe. They did not appear in some pre-existing arena. They are the arena. Asking where the universe appeared is like asking what is north of the North Pole. The question contains an assumption that is simply not valid. North is defined on the surface of the Earth. The North Pole is the northernmost point. There is no north of the North Pole, because north does not extend beyond that point. Similarly, where is defined within space. Space began with the Big Bang. There is no where outside of space. The question is meaningless. Now, I want to take a brief detour into something that might seem like a contradiction of everything I have been saying, because good science means confronting apparent contradictions honestly. The CMB, as I mentioned, is almost perfectly uniform. Almost, but not quite. There is a very slight asymmetry in the CMB temperature. In the direction of the constellation Leo, the CMB is very slightly hotter than average, and in the opposite direction, it is very slightly cooler. This is called the CMB dipole. The temperature difference is tiny, about 3.36 millikelvin, but it is there. Does this not suggest a preferred direction in the universe? Does this not hint at a center? No. The CMB dipole is not a property of the universe. It is a property of our motion. The Earth is moving. The Sun orbits the galactic center. The Milky Way is moving within the local group of galaxies. The local group is moving within the larger Virgo supercluster. All of these motions add up. The net result is that our solar system is moving at approximately 620 kilometers per second relative to the CMB. This motion creates a Doppler effect. In the direction we are moving toward, the CMB light is slightly blue shifted, making it appear hotter. In the direction we are moving away from, the CMB light is slightly red shifted, making it appear cooler. If you subtract this motion, if you mathematically remove the Doppler effect of our velocity, the CMB dipole disappears, and the CMB becomes perfectly uniform. The dipole tells us about our motion, not about the universe's structure. It is not pointing toward a center, it is pointing in the direction we happen to be moving. There has also been some intriguing discussion about something called dark flow, a controversial claim that galaxy clusters across large volumes of space seem to be moving in a coordinated direction, as if being pulled by something massive beyond our observable universe. If this were confirmed, it might suggest some large-scale asymmetry, some departure from perfect isotropy. But the evidence for dark flow is highly contested. Several independent studies have failed to confirm it, and the current consensus is that dark flow, if it exists, is at best a marginal effect. And even if it were real, it would not create a center. It would suggest some influence from beyond our horizon, but without a center within our observable universe. Let me now take you into the fascinating world of cosmic topology. Geometry, as I discussed, tells us about the local curvature of space. Is it flat, positively curved, or negatively curved? But topology tells us about the global structure of space. How is space connected? What is its overall shape? And these are different questions. A flat piece of paper and a flat cylinder have the same local geometry, both flat but different topologies. The paper has edges, the cylinder has one dimension that wraps around. A flat torus, a donut shape, is also locally flat, but has both dimensions wrapping around. You could live on a flat torus, and every experiment you do locally would tell you space is flat, but if you traveled far enough in any direction, you would come back to where you started. The question of the universe's topology is one of the most fascinating open questions in cosmology. Our measurements tell us the universe is locally flat, but they do not tell us how it is connected on the largest scales. The universe could be infinite and simply connected, extending forever in every direction with no wraparound. This is the simplest possibility and is consistent with all current data. But the universe could also be finite and multiply connected, with a topology like a torus, where traveling far enough in one direction brings you back to your starting point. Several specific topological models have been proposed and tested. One particularly interesting one is the Poincaré dodecahedral space, proposed by Jean-Pierre Luminet and colleagues in 2003. In this model, the universe has the shape of a regular dodecahedron, a 12-sided polyhedron, with opposite faces identified, meaning if you exit through one face, you re-enter through the opposite one. This model makes specific predictions about the CMB that can be tested. The results have been tantalizing but inconclusive. Neither this model nor any other non-trivial topology has been confirmed, but neither have they been definitively ruled out. And here is the key point for our purposes. Regardless of the topology of the universe, there is no center. A torus has no center on its surface. A dodecahedral space has no center within it. A Klein bottle, an even more exotic topology, has no center. Every possible topology that is consistent with the observed homogeneity and isotropy of the universe is a topology without a center. The geometry says no center. The topology says no center. The observations say no center. The mathematics says no center. Every avenue we explore leads to the same conclusion. Let me talk about the large-scale structure of the universe, because when you first hear that the universe is homogeneous and isotropic, you might be skeptical. After all, the universe does not look uniform when you look at it. There are stars and planets and galaxies and galaxy clusters and vast empty voids. How can the universe be the same everywhere when it clearly has structure? The answer lies in scale. On small scales, the universe is lumpy, very lumpy. Here is a planet. There is empty space. Here is a star. There is a void. Here is a galaxy. There is a gap between galaxies. But as you zoom out, as you look at larger and larger scales, the lumpiness evens out. It is like looking at a sandy beach. Up close, you see individual grains of sand, each one different, each one at a different position. The beach is lumpy, but from an airplane, the beach looks smooth and uniform. The individual grains are invisible. The lumpiness has been averaged out. The universe works the same way. On scales of hundreds of millions of light years and above, the universe is smooth and uniform. The density of galaxies, the distribution of matter, the properties of space all average out to the same values everywhere. This has been confirmed by massive galaxy surveys like the Sloan Digital Sky Survey, which has mapped the positions of millions of galaxies in 3 dimensions. The maps reveal a breathtaking structure called the cosmic web, a vast network of galaxy filaments, walls, and clusters surrounding enormous, empty voids. It looks like a 3-dimensional spiderweb or like the structure of a sponge, and it is beautiful. But when you zoom out far enough, the web becomes uniform. The density of filaments and voids is the same in every direction. The cosmic web has no center. It has no preferred location. It is a self-similar pattern that extends as far as we can observe. There have been some challenges to this picture. Astronomers have discovered some incredibly large structures in the cosmic web. Structures so big that they push the limits of the cosmological principle. The Hercules Corona Borealis Great Wall, discovered in 2013 through observations of gamma-ray bursts, appears to span about 10 billion light-years. This is enormous, larger than what most cosmological models predict should exist. The giant arc, discovered in 2021, spans about 3.3 billion light-years. These structures have raised questions about whether the universe really is homogeneous on the scales the cosmological principle claims. But the current consensus is that these structures, while surprisingly large, do not violate the cosmological principle at the broadest scales. They are like unusually large waves on an otherwise calm ocean. They are noteworthy, they are interesting, they push our models, but they do not create a center or a preferred location. The ocean is still uniform when viewed from space, even if individual waves are bigger than expected. Now, I want to take you somewhere truly deep. I want to talk about what all of this means, not just scientifically, but philosophically, existentially, personally. Because the idea that the universe has no center is not just a dry fact about geometry and physics. It is a statement about our place in existence. And it is one of the most profound statements that science has ever made. Throughout human history, we have systematically removed ourselves from the center. Earth was the center, then it was not. The sun was the center, then it was not. The Milky Way was the center, then it was not. And now we have learned that there is no center at all. This progression, this steady demotion of human significance, is sometimes called the Copernican principle, in honor of the man who started it all. And the Copernican principle says, in its most general form, that we do not occupy a special position in the universe. We are not at the center. We are not at the edge. We are not in a particularly unusual location. We are ordinary. Our star is ordinary. Our galaxy is ordinary. Our position in the cosmos is ordinary. This can feel depressing. It can feel like science is stripping away our significance, reducing us from cosmic protagonists to cosmic extras, from the center of the story to a footnote in a chapter that no one will read. And this feeling is understandable, deeply, profoundly understandable, because our entire evolutionary heritage has primed us to believe we are important. We are the descendants of organisms that fought desperately to survive, that valued their own existence above all else. Of course, we want to be at the center. Of course, we want the universe to revolve around us. But the universe does not care what we want. It simply is what it is. And what it is centerless. But I want to offer you a different way of looking at this, because I do not think the absence of a center is depressing at all. I think it is one of the most beautiful and liberating ideas imaginable. If there is no center, then no place is more important than any other. Every point in the universe is equivalent. Every location is as central or as peripheral as every other location. This means that wherever you are as much at the heart of the universe as anything or anyone else. You are not at the edge of significance. You are not in the cosmic cheap seats. You are right here, in the middle of everything, because everywhere is the middle of everything. The universe has no center, which means every point is the center. You are the center, and so is the person sitting next to you, and so is the most distant star, and so is the emptiest void. There is a radical democracy to this. The universe plays no favorites. It elevates no one. It diminishes no one. It treats every point, every particle, every galaxy with perfect impartial equality. If that is not beautiful, I do not know what is. Carl Sagan understood this perhaps better than anyone. In 1990, the Voyager 1 spacecraft, at Sagan's request, turned its camera around and took a photograph of Earth from a distance of about 6 billion kilometers. In that photograph, Earth appears as a tiny pale blue dot, barely visible in a beam of scattered sunlight. Sagan wrote about this photograph in terms that still give me chills. "Look again at that dot," he said. "That's here. That's home. That's us. On it. Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. On that tiny dot, floating in the vastness of space, with no special position, no cosmic significance, just a mote of dust suspended in a sunbeam. And yet, on that mote of dust, conscious beings arose who could look up at the night sky and figure out that the universe has no center. Is that not, in its own way, the most extraordinary thing in the universe? The cosmos created beings who could understand the cosmos. The universe generated the intelligence needed to understand itself. We are the universe looking at itself. We are the cosmos becoming conscious. We are atoms that learn to think, stardust that learn to wonder. And in a universe without a center, perhaps consciousness itself is the closest thing to a center there is. Not a physical center, not a spatial center, but a center of meaning, of experience, of understanding. The universe has no center, but your experience of the universe has a center, and that center is you. Not in the arrogant, geocentric way of ancient astronomers, but in the humble, beautiful, existential sense. You are the point at which the universe becomes aware of itself. And that, I think, is far more significant than being at the physical center of anything. I want to ask you something again right now, wherever you are. Drop a comment and tell me how this video is making you feel. Tell me if these ideas are new to you, or if you have thought about them before. Tell me where you are watching from. I love reading comments from people all over the world because it reminds me that our shared curiosity about the cosmos transcends borders and languages and cultures. Science is the most universal language we have. And if you are finding this video valuable, please share it with someone who would appreciate it. Send it to a friend. Post it on your social media. These ideas are too beautiful to keep to yourself. And if you have not subscribed yet, come on, what are you waiting for? We are on this cosmic journey together, and there is still so much more to explore. Let me now take you into an area that blends physics with philosophy in a way that I find particularly fascinating. The arrow of time. We have established that there is no center in space. But what about time? If there is no center in the spatial dimensions, is there a center in the temporal dimension? The Big Bang happened 13.8 billion years ago. It is, as far as we know, the beginning of time. Not the beginning of events within time, but the beginning of time itself. Before the Big Bang, time did not exist. The phrase "before the Big Bang" is as meaningless as north of the North Pole. Time has a beginning, but does time have an end? If the universe continues to expand forever, as current evidence suggests, then time extends infinitely into the future. So we have a beginning, but no end. Can we define a center of time? If time stretches from zero to infinity, there is no midpoint. You cannot find the center of a half-infinite timeline. The concept is undefined. But what if time is not what we think it is? Einstein's theories suggest that time is far more flexible and strange than our everyday experience leads us to believe. In the block universe interpretation of Einstein's relativity, the past, the present, and the future all exist simultaneously. They are all equally real. The universe is not something that unfolds moment by moment. It is a four-dimensional block, a static structure in which time is just another dimension, like length or width or height. In this view, there is no flow of time. There is no privileged moment of now. Every moment is equally real, equally present, equally existent. And in a four-dimensional block with no privileged moment, the concept of a center of time is just as meaningless as the concept of a center of space. There is no special moment in the middle. Every moment is equivalent. Roger Penrose has proposed an even more exotic possibility called conformal cyclic cosmology. In this model, the end of the universe, the heat death, is conformally equivalent to a Big Bang. The infinite future of one cosmic era becomes the beginning of the next. Time is not a line, it is a circle, and a circle has no center. Under this model, the universe cycles through endless aeons, each one ending in a heat death that seamlessly becomes the Big Bang of the next aeon. There is no beginning, no end, and no center. Time itself is centerless, just like space. Now, one concept that is deeply related to the center question is the anthropic principle, and I want to discuss it because it adds an important nuance. The anthropic principle comes in several flavors, but the basic idea is this. The physical constants of the universe appear to be fine-tuned for the existence of life. The strength of gravity, the mass of the electron, the strength of the nuclear forces, the rate of expansion of the universe, all of these values fall within a very narrow range that allows for the existence of stars, planets, chemistry, and ultimately, life. If any of these constants were even slightly different, the universe would be a sterile, lifeless void. No stars, no planets, no carbon, no water, no DNA, no brains, no one to ask where the center is. The weak version of the anthropic principle simply notes that since we exist, we must find ourselves in a universe compatible with our existence. This is almost trivially true, but has important implications. It means that we should not be surprised that the universe has properties suitable for life, because if it did not, we would not be here to be surprised. The strong version goes further and suggests that the universe must have properties that allow the development of consciousness. This is more controversial and veers into philosophical territory. How does the anthropic principle relate to the center question? It tells us that our location in the universe is not entirely random. We are not at the center, but we are also not at a random location. We are at a location where conditions are right for life. We are on a rocky planet at the right distance from a stable star, in a region of a galaxy that is neither too dense nor too sparse, in a universe that is old enough for heavy elements to have been forged in stellar furnaces and dispersed by supernova explosions. We are where we need to be, not at a center, but in a habitable niche. And this habitable niche is not unique. There are likely billions of similar niches in our galaxy alone, and trillions upon trillions throughout the observable universe. Our niche is not special. Our location is not special. We are at a center only of our own experience, not of the cosmos. Let me present some thought experiments that might help crystallize these ideas. Imagine you had a magic teleportation device that could transport you instantly to any point in the universe, any point at all. Where would you go to find the center? Let us say you pick a direction and teleport 10 billion light years away. You arrive, you look around, and what do you see? Galaxies in every direction. The CMB uniform in every direction. The same expansion, the same physics, the same laws of nature. Everything looks exactly as it does from Earth. You are not at the center, but everything around you is identical to what you left behind. So you teleport another 10 billion light years. Same thing. Galaxies. CMB. Expansion. Uniformity. You keep going. 100 billion light years. A trillion. Assuming the universe is infinite, you can keep going forever and you will never find a center. Every place looks like every other place. There is no landmark, no beacon, no sign that says, "Center of the universe." You are here. The universe is like an infinite desert with perfectly uniform sand in every direction. There is no oasis. There is no landmark. There is no center. Just sand forever in every direction. Now imagine a different thought experiment. Imagine the universe is finite but without boundaries, like the surface of a very large sphere, except in 3 dimensions instead of 2. You start walking in one direction, a perfectly straight line, and you keep walking forever. What happens? Eventually, after traversing the entire circumference of this hypersphere, you arrive back at your starting point. You have gone all the way around the universe and come back. And at no point during your journey did you encounter an edge. At no point did you pass through a center. The center of the hypersphere is in the 4th spatial dimension, in a direction perpendicular to all 3 spatial dimensions you can perceive, in a place you can never go and can never point to. For you, a 3-dimensional being on the 3-dimensional surface of a 4-dimensional hypersphere, the center does not exist in any meaningful sense. It is outside of your reality. It is like asking a flatworm crawling on the surface of a basketball where the center of the basketball is. The flatworm cannot even conceive of the answer because the answer lies in a dimension the flatworm does not have access to. We are that flatworm. The universe is that basketball. Except we are not sure the basketball even has an interior. The surface might be all there is. Here is another thought experiment that I find particularly illuminating. Imagine you could somehow see the entire universe all at once, from the outside, like a god looking down at creation. What would you see? If the universe is infinite, you would see an infinite expanse of galaxies, uniformly distributed, stretching forever in every direction. There is no center to an infinite expanse. There is no edge. There is no shape. It just goes on and on and on. If the universe is finite and closed, you would see a three-dimensional hypersphere, like a four-dimensional ball. From the outside, yes, you could identify the geometric center of the ball. But that center is in the fourth dimension. It is not on the three-dimensional surface where everything actually exists. It is not in the universe. It is outside of it. And for the beings living in the universe on the surface, the center is inaccessible and irrelevant. It is as meaningful to them as the geometric center of the Earth is to someone sailing on the ocean. Yes, the center of the Earth exists, but it has nothing to do with the surface of the ocean. The ocean has no center. The surface of the Earth has no center, and the surface of the universe has no center. Let me now bring you up to speed on the latest scientific observations and what they tell us about this question. The James Webb Space Telescope, launched in December 2021 and operational since mid-2022, has been peering deeper into the universe than any instrument before it, observing galaxies that formed within the first few 100 million years after the Big Bang. Some of these early galaxies are surprisingly massive and mature, more developed than our models predicted they should be at such an early stage. This has challenged some aspects of our models of galaxy formation and evolution, but it has not changed the fundamental conclusion about the center. If anything, the observation that galaxies formed so early and so universally reinforces the homogeneity of the universe. Structure emerged everywhere, not from a center. The JWST observations confirm that wherever we look, at whatever distance, the universe is doing the same things, forming galaxies, igniting stars, building the same cosmic web, the same processes, the same physics, the same universe in every direction. No center. The dark energy spectroscopic instrument known as DESI has been creating the most detailed three-dimensional map of the universe ever made, measuring the positions and redshifts of tens of millions of galaxies, quasars, and other objects. The preliminary results from DESI have been fascinating, with some hints that dark energy might not be a simple cosmological constant after all, that it might be changing over time. If confirmed, this would be a major discovery that could reshape our understanding of cosmic expansion. But even a time-varying dark energy does not change the fundamental symmetry of the universe. The expansion might be changing, but it is changing the same way everywhere. No center. Gravitational wave astronomy, which began in earnest with the first detection by LIGO in 2015, has opened a completely new window on the universe. Gravitational waves, ripples in the fabric of spacetime itself, have been detected from merging black holes and neutron stars throughout the cosmos. And here, too, the message is the same. Gravitational wave sources are distributed uniformly across the sky. There is no preferred direction. There is no concentration toward a center. The universe is isotropic, even in the language of gravitational waves. Future missions will push these observations even further. The Euclid Space Telescope from the European Space Agency, the Nancy Grace Roman Space Telescope from NASA, and the Vera Rubin Observatory on the ground will map the universe with unprecedented precision, measuring the shapes and positions of billions of galaxies, probing the nature of dark energy, testing the cosmological principle with ever greater rigor, and I am confident as a scientist can be, that they will confirm what we already know. The universe has no center, it never had a center, and it never will have a center. But let me be honest with you, because honesty is the foundation of science. We could be wrong. Our models could be incomplete. General relativity could be an approximation of a deeper theory, just as Newtonian gravity was an approximation of general relativity. The cosmological principle could be violated on scales larger than we can currently observe. There could be a center out there somewhere beyond our cosmic horizon, undetectable with current technology. I consider this unlikely, but I cannot rule it out with absolute certainty. And this is what I love about science. It is humble. It does not claim absolute truth. It claims the best current understanding based on available evidence. And the best current understanding, supported by the CMB, by galaxy surveys, by general relativity, by inflation theory, by the Hubble expansion, by every piece of data we have, is that the universe has no center. If tomorrow someone discovered evidence of a center, science would change, models would be revised, theories would be updated. That is not a weakness of science. It is its greatest strength. Science is not a collection of facts carved in stone. It is a living, breathing, self-correcting process of discovery. And right now, that process is telling us loudly and clearly that the center does not exist. Let me take you on one more detour before we begin wrapping up. I want to talk about what the absence of a center means for some deep questions about the nature of reality itself. Some physicists and philosophers have proposed that our universe might be a simulation. This idea, while speculative, is taken seriously by some thinkers because of arguments about the statistical likelihood of simulated universes versus base reality universes. If our universe is a simulation, could it have a center? After all, the computer running the simulation must be somewhere. The server room has a physical location. Does that make the server room the center of the simulated universe? This is an interesting question, but the answer, I think, is no. Even in a simulation, the physics can be centerless. The rules of the simulation can be uniform and isotropic, just like the rules of a non-simulated universe. The server room is not in the simulation. It is outside of it, in a different layer of reality. From the perspective of beings within the simulation, their universe has whatever properties the simulation dictates. And if the simulation dictates a homogeneous, isotropic, expanding universe, then for all practical purposes, their universe has no center, regardless of what is going on outside. I also want to touch on something that might have been nagging at you throughout this video. I have been saying that the universe has no center. But I have also been describing a universe that started from a singularity, a point-like state. How can something start from what seems like a single point and not have that point as its center? The resolution lies in understanding what the singularity really means. In the equations of general relativity, the singularity is a point where the equations break down. The density becomes infinite. The curvature of spacetime becomes infinite. The physics, as we understand it, ceases to give meaningful answers. The singularity is not a well-defined physical state. It is a mathematical indication that our theory is incomplete. At the very earliest moments of the Big Bang, within the first Planck time, which is about 5.39 times 10 to the power of negative 44 seconds, general relativity cannot be trusted. We need a theory of quantum gravity, a theory that merges general relativity with quantum mechanics to describe what happened, and we do not yet have such a theory. Loop quantum gravity string theory, and other approaches offer glimpses and hints, but none has been confirmed. So, when I say the universe started from a singularity, what I really mean is that the universe was once in an extremely hot, dense state, and our current theories cannot describe the very earliest moments. The singularity might not have been a literal point. It might have been a quantum state without a well-defined geometry. It might have been a state in which the very concepts of space and time did not yet apply. The singularity is not a place. It is a limit of our knowledge, and this makes the question of a center even more clearly meaningless. The starting point of the universe is not a point in the normal sense. It is a breakdown of physics. You cannot build a center from a breakdown. There is a concept in mathematics and physics called gauge invariance, and while it is technical, the basic idea is relevant here. Many physical theories have a property where you can change certain aspects of the mathematical description without changing the physics. These changes are called gauge transformations. In general relativity, there is a gauge freedom related to coordinates. You can choose any coordinate system you like to describe spacetime, and the physics does not change. There is no preferred coordinate system. There is no correct set of coordinates. This is related to the idea that there is no center, because a center would be a special point in some coordinate system, and the principle of gauge invariance says that no coordinate system is more correct than any other. You can put the origin of your coordinate system anywhere you want, and the physics looks the same. This is a deep, fundamental symmetry of the universe, and it directly implies that no point is special. No point is the center. Let me also address the concept of symmetry more broadly, because symmetry is the deep reason why the universe has no center. In physics, symmetries are not just aesthetic properties. They are connected to conservation laws through a mathematical theorem called Noether's theorem, discovered by the brilliant mathematician Emmy Noether. Noether's theorem says that every continuous symmetry of the laws of physics corresponds to a conserved quantity. The symmetry of physics under time translation, the fact that the laws of physics are the same today as they were yesterday, corresponds to the conservation of energy. The symmetry of physics under spatial translation, the fact that the laws of physics are the same here as they are over there, corresponds to the conservation of momentum. And this spatial translation symmetry, this homogeneity, is directly related to the absence of a center. If the laws of physics are the same everywhere, then no place is special. No place is the center. Homogeneity implies no center. And since homogeneity is a fundamental symmetry of the universe, verified by observation to extraordinary precision, the absence of a center is not just a fact. It is a consequence of the deepest symmetries of nature. Now, I want to address something that might be lurking in the back of your mind. A feeling, an emotional response to everything I have been saying. Because learning that the universe has no center can trigger a complex mix of emotions. For some people, it provokes wonder and awe. The sheer scale of the cosmos, its perfect democracy of space, its infinite expanse without edge or center, can be breathtaking. For others, it provokes anxiety. If the universe has no center, if we are not special, if there is no preferred location, then what does it all mean? Where do we fit? What is our purpose? And for still others, it provokes a kind of existential vertigo. a dizzying sense of groundlessness, of floating in an infinite void with no anchor, no reference point, no center to hold on to. All of these responses are valid. All of them are human. And I want to sit with that for a moment. The universe is under no obligation to make us comfortable. It is under no obligation to organize itself in a way that satisfies our need for significance. But we are under an obligation to ourselves to find meaning despite, or perhaps because of, the universe's indifference. And I believe that a centerless universe is not a meaningless universe. Let me tell you why. In a universe with a center, significance would be easy. The center would be special, the edge would be marginal, meaning would be imposed by geometry. But in a universe without a center, significance must be created. It must be chosen. It must be built by conscious beings who look at the cosmos and decide that their lives matter, not because the universe says so, but because they say so. This is the existentialist insight of Sartre and Camus, translated into cosmological terms. Existence precedes essence. The universe exists without inherent purpose, without a center, without a plan. And we, products of this universe, create our own purpose, our own center, our own meaning. The absence of a cosmic center is not a void. It is a freedom. It is the freedom to create our own center wherever we happen to be. And there is a beautiful paradox here. The universe has no center, but consciousness creates a center. Your awareness, your experience, your perspective, these create a center that is uniquely and entirely yours. You see the universe from your position, through your eyes, with your mind, and from that position, you are at the center of everything you will ever experience. Not because the universe put you there, but because that is how consciousness works. You are always at the center of your own experience, and so is every other conscious being. We are all at the center. None of us is at the center. Both are true simultaneously, and I find that to be one of the most beautiful paradoxes in all of philosophy. I want to circle back now to something I mentioned earlier, the idea of the cosmic web and the large-scale structure of the universe, because there is a feature of this structure that is particularly relevant to our meditation on centers. The cosmic web is organized around vast empty regions called voids. These voids are the emptiest places in the universe, hundreds of millions of light years across, containing almost no galaxies. The galaxies are concentrated in the filaments and walls that surround the voids, like the walls of a sponge surrounding the air pockets. Now, you might think that the biggest void, or the densest supercluster, could serve as a kind of center, but there is no biggest void. There is no densest supercluster. The voids and the filaments are distributed uniformly, on average, throughout the entire universe. Our own cosmic address gives you a sense of this. Earth is in the solar system, which is in the Milky Way galaxy, which is in the local group of galaxies, which is in the Virgo supercluster, which is part of an even larger structure called the Laniakea supercluster, discovered in 2014 by Brent Tully and colleagues. Laniakea spans about 500 million light years and contains about 100,000 galaxies. It is defined by the flows of galaxies, all being drawn toward a region called the Great Attractor, a concentration of mass in the direction of the constellation Centaurus. The Great Attractor might sound like a center, but it is not. It is just a local concentration of mass, a large-scale version of a mountain on Earth. Earth has mountains and valleys, but no one would call a mountain the center of the planet. Similarly, the great attractor is a feature of the cosmic landscape, not a center of the universe. Beyond Laniakea, there are other superclusters. The Shapley supercluster, the Perseus-Pisces supercluster, the Horologium supercluster, they are all around us in every direction, part of the great cosmic web that spans the observable universe. And they are all equivalent. None is the center. None is more important. They are all just features on the vast, uniform, centerless landscape of the cosmos. Let me take you through one more layer of physics that I think is important for this topic. The relationship between quantum mechanics and the absence of a center. Quantum mechanics, the physics of the very small, seems at first glance to be unrelated to cosmology, the physics of the very large. But the two are deeply connected, and their intersection reveals something profound about the nature of reality. In quantum mechanics, the principle of translation invariance states that the laws of quantum physics are the same at every point in space. If you set up an experiment here and an identical experiment a billion light years away, the results will be governed by the same quantum mechanical laws. This is the quantum version of homogeneity, and it implies, at the most fundamental level of physics, that no point in space is special. Quantum mechanics does not know about a center. The wave functions of particles, the probabilities of interactions, the rules of quantum field theory, all are translation invariant. The microscopic world confirms what the macroscopic world tells us. There is no center. At no scale, from the subatomic to the cosmic, does a center emerge. The universe is centerless from top to bottom, from the smallest quantum fluctuation to the largest cosmic structure. And quantum mechanics plays another role in this story. The tiny fluctuations in the CMB, those 1 in 100,000 variations in temperature that were the seeds of all cosmic structure, originated as quantum fluctuations. In the extremely early universe during inflation, random quantum fluctuations in the energy of the inflaton field were stretched by the exponential expansion to cosmic scales. These fluctuations became slight variations in the density of matter, which became slight variations in the gravitational pull, which became the seeds around which gas condensed to form galaxies and galaxy clusters and the entire cosmic web. The structure of the universe, the galaxies we see, the web they form, all of it traces back to random quantum noise from the inflationary era. And because these fluctuations were random, they had no preferred center. Random noise, by definition, has no center. It is the same everywhere. Statistically, the seeds of structure were uniform. The growth of structure was uniform, and the resulting universe is, on large scales, uniform, centerless from the very first quantum flutter to the present day. I am going to share something personal with you now, or as personal as a discussion about cosmology can get. The idea that the universe has no center changed my life. I know that sounds dramatic. I know it sounds like an exaggeration, but it is true. When I first truly understood this idea, not just intellectually, but in my bones, in my gut, in the deep place where understanding becomes feeling, something shifted inside me. I had grown up, like most people, with an implicit sense that the universe had a structure that meant something, that somewhere out there was a center, a heart, a core, a place where everything began and to which everything might return. And learning that this place does not exist was initially disorienting. It was like finding out that the building you live in has no foundation. How can it stand? How can anything stand? But then I realized something. A building needs a foundation because gravity pulls it down. But the universe is not a building. It does not need a center for the same reason a river does not need a source to flow. Wait, rivers do have sources. Bad analogy. The universe is not like anything. It is unique. It is the only thing of its kind that we know of, and its rules are its own. It does not need a center to exist. It does not need a preferred point to be coherent. It simply is, everywhere, equally, completely. And once I accepted that, once I let go of the need for a center, I found a different kind of peace. Not the peace of being at the center of something, but the peace of being part of everything, equally, without hierarchy, without favoritism, without the anxiety of being close to or far from some cosmic heart, just being here, part of it all. Before we reach the conclusion, I want to address a few more subtle points that I think are important for a truly complete understanding of this topic. The first is the concept of the Hubble flow. The Hubble flow is the general expansion of the universe, the tendency of all distant objects to recede from each other due to the expansion of space. Galaxies that are participating in the Hubble flow are called co-moving objects. They are not moving through space. They are moving with space as it expands. The concept of co-moving coordinates is important because it provides a natural framework for describing the universe. In co-moving coordinates, galaxies are essentially stationary. Their coordinates do not change. What changes is the scale factor, a mathematical quantity that describes how much the universe has expanded. As the scale factor increases, the physical distances between co-moving objects increase even though their coordinates stay the same. In co-moving coordinates, the universe looks the same at every point. Every co-moving observer sees the same expansion, the same CMB, the same physics. No co-moving observer is at the center. The co-moving coordinate system has no origin, no preferred point. Any point can be chosen as the origin, and the physics looks identical. The second subtle point is about the distinction between physical and mathematical centers. In mathematics, any coordinate system has an origin, a point labeled 0. You could label any point in the universe as the origin of your coordinate system and call it the center. But this would be completely arbitrary and physically meaningless. It would be like declaring your living room to be the center of the earth because you decided to measure all distances from there. You can do it, but it does not make your living room physically special. The center of a coordinate system is a mathematical convenience, not a physical reality. The universe has no physical center, even though you can always choose a mathematical center by picking an arbitrary origin for your coordinates. The third subtle point concerns the difference between local and global properties. Locally, the universe has lots of structure. There are planets, stars, galaxies, clusters, voids. These create local centers in the sense that every gravitationally bound system has a center of mass. The solar system has a center of mass, roughly at the center of the Sun. The Milky Way has a center of mass, roughly at the supermassive black hole, Sagittarius A star. The local group has a center of mass somewhere between the Milky Way and Andromeda. These local centers are real and physically meaningful, but they are not the center of the universe. They are the centers of local systems, no more cosmically significant than the center of a grain of sand on a beach is significant to the entire beach. The beach has no center, even though every grain of sand in it does. And the fourth subtle point is about the relationship between the center of the universe and the origin of the universe. People often conflate these two concepts. They think that the center of the universe should be the place where it started. The origin, in both senses of the word. The origin in time and the origin in space. But as I have explained, the Big Bang did not have a location. It happened everywhere. So the temporal origin of the universe is not a spatial point. The beginning of time is not a place. It is a moment that occurred everywhere simultaneously. You cannot visit the place where the Big Bang happened by traveling through space, because the Big Bang happened at every place. You can visit the time when the Big Bang happened by looking far enough away, because looking far away is looking back in time. And when you look as far as possible, you see the CMB, the echo of the Big Bang. But the CMB surrounds you in every direction equally. It does not come from a point. It comes from everywhere. The beginning of the universe is not a location. It is a sphere of ancient light surrounding every observer, equally, uniformly, without center. Now, I want to take you through one final extended thought that I have been building toward throughout this entire video. And I want you to really sit with this one. Let it permeate. Let it settle into your understanding. Because I think it is the most profound implication of everything we have discussed. The universe is 13.8 billion years old. It contains roughly 2 trillion galaxies in the observable volume alone. Each galaxy contains hundreds of billions of stars. Many of those stars have planets. The total number of planets in the observable universe is estimated to be in the range of 10 to the power of 24, or a trillion. The total number of atoms in the observable universe is estimated to be about 10 to the power of 80. The observable universe has a radius of about 46.5 billion light-years. And beyond the observable universe, the actual universe might be vastly larger, perhaps infinitely larger. In this incomprehensibly vast arena, there is no center, no point of origin, no heart, no core, no place where a sign reads, "You are here at the center of everything." And yet, here you are, reading this, thinking about this, contemplating the nature of the cosmos from a planet orbiting a star in a galaxy, in a supercluster in the cosmic web. And you are conscious, you are aware, you are experiencing this moment, this thought, this idea. And in the entire observable universe, with its 2 trillion galaxies and its trillion planets and its 10 to the 80 atoms, consciousness is rare, extraordinarily, unimaginably, heartbreakingly rare. We do not know how rare. We do not know if we are the only conscious beings in the cosmos, or one of millions of conscious civilizations, or somewhere in between. But we know that the vast majority of the universe is empty space, and most of the matter is dark matter that does not think, and most of the energy is dark energy that does not feel. The universe, in its overwhelming majority, is unconscious. It does not know it exists. It does not care that it has no center. It does not wonder about its own origin or its own fate. It simply is. But we care, we wonder, we know. And that, I would argue, is what makes us significant. Not our location, which is ordinary. Not our star, which is common. Not our galaxy, which is unremarkable. But our consciousness, which, as far as we know, is extraordinary. In a universe without a center, consciousness is the closest thing to a center there is. It is where the universe turns around and looks at itself. It is where matter contemplates its own existence. It is where atoms, forged in the hearts of ancient stars, have organized themselves into structures so complex that they can ask the question, where is the center? And the answer, as we now know, is that the center does not exist. But the question does, and the beings who ask it do. And perhaps that is enough. Perhaps in a universe without a center, the most meaningful thing that can happen is for conscious beings to arise and ask questions about the cosmos, to probe its secrets, to map its structure, to understand its laws, to feel awe at its beauty, to feel humble before its immensity, to feel connected to its fabric. Because we are not observers of the universe. We are part of it. We are made of it. The atoms in your body were forged in the cores of stars that exploded billions of years ago. The iron in your blood came from a supernova. The calcium in your bones came from the death throes of ancient stars. The hydrogen in your water has been around since the first moments of the Big Bang. You are not separate from the universe. You are the universe looking at itself. You are the cosmos, conscious. You are the void, aware. And in a universe with no center, you are as central as anything can possibly be. I want to now share with you a meditation that I think captures the spirit of everything we have discussed. It is a way of seeing the universe that I return to often. When the scale of the cosmos threatens to overwhelm me, when the absence of a center threatens to feel like an absence of meaning. Close your eyes if you can and imagine the following. You are floating in space, not near any star, not near any galaxy, just floating. Around you in every direction, galaxies stretch to infinity. Billions of them, trillions of them, each one a vast island of stars, and they are all moving away from you, not because you are at the center, not because you are special, but because space itself is expanding everywhere equally. You look to the left, galaxies are receding. You look to the right, galaxies are receding. You look up, galaxies are receding. You look down, galaxies are receding. You are at the center of your visible cosmos, but this is an illusion of perspective, not a truth of physics. Because if you were to teleport to any of those distant galaxies, the view would be the same. Galaxies receding in every direction, you at the center of a new visible cosmos, and an alien on that galaxy, looking toward where you used to be, would see your old position receding from them. Everyone is at the center. No one is at the center. The two statements are the same statement, viewed from different angles. And in this cosmic democracy and this perfect equality of all positions and all perspectives, there is a profound lesson. No place is special. No being is cosmically privileged. The universe does not favor you or me or anyone. And in that impartiality, in that perfect indifference, there is a strange and beautiful peace. Because if the universe does not tell you where the center is, then you are free to decide for yourself. And you can decide that the center is here, wherever here is. You can decide that the center is now, whenever now is. You can decide that the center is you, whoever you are. Not because the universe says so, but because you say so. And in a cosmos without a center, your decision is as valid as anyone else's. That is the democracy of a centerless universe. That is the freedom of an infinite cosmos. That is the beauty of a truth that does not care about your feelings, but nonetheless leaves room for all of them.